So let's start the seminar. Then it's my great pleasure to present Clara Löh from University of Regensburg. She'll talk about simplicial volume of unrelated groups. Please.
Yes, thank you very much. Thanks for the kind invitation. We already talked about this before, so this is a first for me, giving a talk in Brazil. It's very nice, and I mean, the few people that I have seen, you have very summer-like clothes on, and here we have ice and snow. It's a bit confusing. Okay, so yeah, I will talk about simplicial volume of one-related groups. All of this is joint work with Nicolaus Heuer, who's a postdoc in Cambridge now. And the plan is I will first talk a little bit about one-related groups, then I will talk about stable commutator length, and in the end about simplicial volume. Okay, so let's start with simple things. So let's start with the one-related groups. Okay, so probably most of you know this, and it's also, I mean, it is exactly what the name says. So a one-related group is just a group that has a presentation with one relator. Okay, so you have a set S, and usually, let's for simplicity assume it's finite, and we have one relator. So that's something that lives in the free group freely generated by S. And I will always denote this by F. Okay, so by definition, this is just, we take this free group and then we divide out the normal subgroup generated by the relator. Okay, so yeah, it's just a class of groups. Let's look at some simple examples to get a little bit of a feeling for these groups. So let's do a super easy example, right? If I have one generator A and I divide out the relation A squared, then of course I get Z mod 2. Okay. Then what else is a reasonable thing would be to take two generators A and B and then divide out the commutator of A and B, and then of course we get Z squared. Okay, and then if we like continue in this way, we add more generators. So we have A1 up to AN, B1 up to BN, and we divide out the single relator that is given by the product of the commutators. So we take the commutators A1, B1, A2, B2, and so on up to AN, BN. Then, of course, this is just the fundamental group of the surface of genus N in this case. And then, of course, I mean, there are lots more examples, like, I don't know, for example, Baumschlag-Solitar groups are an interesting class of groups. And so on. So it's on the one hand, it's like it's a fairly rich class of groups, right? I mean, you can have very already also strange behavior with a single relator, but it's still manageable because you just have one relator and not a chaotic list of relators that interact wildly with each other. Okay, so the question that one could ask is, this is a very general question, and of course there's no general answer, but like the overall question could be to ask, well, somehow, can you read off properties of this group from properties of the relator? So how are properties of this one relator group related to properties of this relator R? Okay, as I said, I mean, the question is far too general, but maybe let's look at some properties that are rather well known and give maybe already some kind of impression on what to expect. Okay, so we're following well-known things, and I think basically all of this is really fairly classical. So, well, we have seen this example where we divide. Like the first example was we have one relator and we have the one generator A, and we divide out the relation A squared. So in this case, the relator is a proper power, and then in this case, at least, you get torsion. And well, one might naively believe if this element is not a proper power, then you don't have torsion. And in fact, this is true. So if R is not a proper power, then the one-relator group SR is torsion-free. And it gets even better. So, well, you could look at the presentation complex. So what's the presentation complex is you take a wedge of circles for every for every generator, you take one circle, and then you add a two-disk. So you add this to this wedge of circles, and well, what you do on the boundary of this two-disk, so this is a D2, is just given by this relator R. Okay, so that's the presentation complex. It's a topological space that you can just construct out of your one relator group. And if R is not a proper power, then this presentation complex is already a classifying space. So then and the presentation complex of this presentation is a classifying space for the group. Yeah, so just a reminder, this means that the fundamental group of this space is the group itself. I mean, this is always true if you have a presentation complex, but the like harder condition to satisfy is that you have no higher homotopy groups, or in other words, that the universe covering is contractible.
May I ask the question here?
Yeah, sure. Yeah.
Would it imply here that it is also homological dimension 2, or one needs more work to deduce?
Well, no, in general, it will not be cohomological dimension 2, but it will be cohomological dimension at most 2, right? I mean, so you could have the silly case.
Yes, I meant at most 2. Yes, at most 2.
Yeah, that you have, yeah, because the classifying space is a model then, and this has dimension 2, and so the cohomological dimension is also at most 2. But of course, you can have the silly case, for example, that the relator R is trivial, and then you have a free group, and then
it's just a generator for free group, yeah.
Yeah, or just a generator, and then you get cohomological dimension 1. Yeah, but you have at most 2. Yeah, let me write this down. So in this case, cohomological dimension of this one related group is at most 2. And in fact, in the cases that we will discuss later, we will have really equality here. Okay, so that's one case. If you have something that's not a proper power, then you have a super nice model of the classifying space. Okay, then conversely, if R is a proper power, okay, so in some sense, you might say, oh, this is not a bad case, but this case is also good, but in a different direction. Then you know that the group is always hyperbolic. So it's a word hyperbolic group in the sense of Gromov. And the way to prove this is just like the things from like classical things from combinatorial group theory show that the Dane's algorithm to solve the word problem works for these groups, and then you know it's hyperbolic. Okay, so that's also a nice feature. Then maybe another thing is that if you're thinking more in terms of geometric group theory, another like the complementary class, so to say, of hyperbolic groups are amenable groups. So you could wonder, when are these one-relator groups amenable? And let's just focus on the case that the relator is in the commutator subgroup. Then the one-relator group is amenable if and only if it's isomorphic to z squared.
We cannot see above below this line actually.
So, and then yeah, another thing is now I mean, in the end I want to move towards homological things, so maybe it's worth thinking about the second homology of the group. So that's like from what I said before, maybe the interesting homology group. And well, the second homology of this one-related group, let's say with integral coefficients, this is isomorphic to Z if the relator was in the commutator subgroup and non-trivial. And well, it's even better than that. I mean, you know exactly how to get this copy of Z. Namely, this is basically generated by the relator in the sense of this presentation complex. Okay. So this is, let's say, it's generated by R. So independently of whether the presentation complex is a model or not, this class that you get from attaching this disk via R in homology is a generator of the second homology. Okay, and because the relator is assumed to be in the commutator subgroup, you really get a homology class. I mean, if the relator is not in the commutator subgroup, then this cell will not define a class in H2. Okay, and the way to prove it, if you're interested, is via the Hopf formula for the second homology. So that allows you to write second homology more or less explicitly in terms of a presentation. Okay, so that's all that I wanted to say generally about one-related groups. So in the following, we focus on the case that the relator is in the commutator subgroup. Okay, because then we have this nice homology class, and there are two invariants that I want to consider. Maybe I also exclude the trivial relator, and following invariants. So you could somehow approach this from the algebraic side and say, oh, let's look at the relator and let's see what we can squeeze out of the relator. And of course, there are many things that you can do. But if you have a relator in the commutator subgroup, then it's particularly tempting to think about the stable commutator length of this relator. So you can look at stable commutator length. And I'll explain in a minute what this is. And on the other hand, if you look at it from a more geometric or homological point of view, you could look at the simplicial volume of this group. And of course, the first one, the stable commutator length, this is an invariant of the relator. And the second one is an invariant of the group. So in this sense, if you figure out how these two things interact with each other, then this is an instance of this question, how properties of the group are related to properties of the relator. Okay, so that's the setup. That's what we want to do. So yeah, let's move on to the second part. I want to talk about stable commutator length. So let me give the definition. Stable commutator length. So for an element G in F, we define first, let's define the commutator length of G. Well, it's also, again, it's a very straightforward definition. I mean, it's exactly what the name says. You just count how many commutators do you need to write your element G. So it's the infimum over all n in n, such that you can find group elements x1 up to xn, yn up to yn, such that you can write your element G as this product of commutators. And of course, well, if your element G is not in the commutator subgroup, then you won't find any of these elements at all. So this might be infinite. And it will be finite if and only if you're in the commutator subgroup, but you can always define it if you want. Okay, so that's the commutator length. And it turns out that even though this is a very nice thing to look at, maybe, it's very hard to compute. So this is very difficult to compute. And there are also precise statements of this type. So, for example, by Nicolaus Heuer, the difficulty of computing commutator length. Okay, and but things get a lot better if you stabilize. So there's a stable commutator length of G. Yeah, well, now instead of looking only at the element G, you look at all its powers. That was too optimistic. At all its powers simultaneously, and you compute the commutator length of these powers. But then, of course, it's wise to normalize by the power, and then you take the infimum over all these numbers. Okay, and that gives something that's a priori. It could be any non-negative real, or if no power ends up in the commutator subgroup, of course, then you get infinity. And yeah, so this is maybe a little bit surprising. This is more or less easy to compute. So, I mean, not by hand, but by a machine. So this can be computed efficiently. And this is due to Caligari. Yeah, so efficiently means there is a polynomial algorithm, and polynomial in the length of the relator, or of the group element. And this is not only a theoretical result. I mean, what use is a polynomial algorithm that has, I don't know, degree 1000. It's not like that. I mean, it's you can use it in practice. It's really, it's a good algorithm in that sense. And moreover, so what he does, in fact, is he shows that you can obtain the stable commutator length as the value of a rational linear optimization problem. So this means that the stable commutator length on the free group only takes on rational values, right? It's not clear from the definition because this infimum could be anything, but it turns out in the free group it's always rational, okay? So let me replace this by the non-negative rationals. Okay. So there are lots of things known about this now, and I think most of it is due to Caligari, or at least initiated by him. So, for example, what is known, that there is a gap. So meaning that for all elements in the commutator subgroup that are non-trivial, the stable commutator length of G is at least 1/2. Okay, and there are lots of things known about the distribution and so on. Lots of computations have been made using this algorithm. So there's a lot known about this, but there's one nice open problem. So at least I like it. And this is about whether there is a second gap. So the question is whether there exists an element in the commutator subgroup such that the stable commutator length of S is bigger than 1/2 and smaller than 7/12. So in all these experiments and in all these computations, the next smallest value that could be realized was the 7/12. So the obvious question is whether this is really a gap, or whether we just didn't find any elements in between. Okay, and maybe also let me give you one example computation. So the stable commutator length, now you can't see this anymore probably, so let me move this up. So the stable commutator length of the thing that you would get for the surface relator so you want to compute stable commutator length of this product of n commutators that all involve different generators, and turns out that this is n minus 1/2. Okay, so that's a computation. I mean, it's not obvious, but this can be shown. Okay, so yeah, that's all that I wanted to say about stable commutator length. So yeah, I'm sorry, the program always moves the page when I save it and export it. This is why the page is now jumping up and down. So I'll now upload this page, and then we will move on to Simplicial volume. Okay, so I'll first talk a little bit about like the general, original, classical Simplicial volume, and then we will return at some point to the one-relator group case. Okay, so yeah, let's start with the definition of Simplicial volume. And this goes back to Gromov at the end of the 70s, and I'll when I give the examples, I'll also tell you the context of when and why he introduced it. So this is invariant of manifolds, so the Simplicial volume of an oriented closed connected n manifold M is defined as follows. So it's just the one norm of the fundamental class, and I'll spell it out in a second what this means. So this means we look at all fundamental cycles of M. So these are linear combinations of real numbers. So this is a real number. And this here is a continuous map from delta n to m. So this is a singular cycle in degree n of m. And it shouldn't be any cycle, but it should be a fundamental cycle. Okay, so I look at all these cycles. Now I want to assign a size to these cycles, and there are many ways of doing this, but there's one way that really doesn't require any geometry or anything. I could just like count the number of simplices, but I also take the weight of the coefficients into account. So I just take the one norm of this chain. So I sum up all the absolute values of the coefficients, and then I optimize over that. So I'm looking for the infimum of this. Okay, so this gives a non-negative real number. Okay, so I don't know, this is an algebra seminar, so I don't know how familiar you are with all these things. So let me just draw one picture and explain it with that a little bit. So we have our manifold, okay. And now let's think about the good case. And the good case is that this manifold even admits a triangulation. Okay, so then I can have my triangulation. Okay, and this triangulation, then this will give a fundamental cycle. And of course, the one norm of this cycle is just the number of top dimensional simplices that I have in my cycle. Okay, so in particular, what I get is that the simplicial volume is always bounded from above by the minimal number of simplices in the triangulation. Okay, so that will be the first property. So let me list some properties. So if M is triangulable, then the simplicial volume of M is bounded from above by the minimal number of n simplices in a triangulation of M. Okay, so that somehow gives a first impression of what this is, but usually you can do much better than that. I mean, because in the definition here, nobody says that the simplices that you use, the singular simplices, that they're actual simplices in the manifold, but you can have like any wild topological simplex. So let me do one example where you can already see what the effect of this is. So if you look at S1, so the circle, okay. So let's look at that. So the circle, of course, the circle admits a triangulation, and if I triangulate it, then I need 3 one simplices. So as a value, I get 3 in this case. But now, since I'm allowed to take singular simplices, I can do better. I could also say, oh, I mean, why should I have 3 of those? I only need 1, okay? So I can just take 1 singular simplex to wrap around the whole circle, okay? But then we have a real coefficient, so we can do even better. So we can walk around the circle twice. Yeah, okay, so now this is not the fundamental cycle because somehow you meet everything twice. So you should correct this by adding a coefficient of 1/2. So in this way, you get 1/2 as the value. And of course, now you can iterate, right? So you can do this, I don't know, d times. So you take 1 over d here, you get 1 over d as the value here, and you see the infimum is 0. So usually you can do much better than triangulations because you have singular simplices. Okay, so that's the circle. Then maybe let's move on to interesting examples. So I think the key example is the hyperbolic case. So if M is hyperbolic, then, okay, the Simplicial volume M is the same as the volume of M, hyperbolic volume, right? The hyperbolic manifold, hyperbolic Riemannian metric has a volume. And well, there's a correction factor, Vn, and this really depends only on the dimension. So this also has concrete geometric meaning. It's the maximal volume of ideal regular simplices in hyperbolic n space. I mean, that's maybe not so relevant, but it's something that only depends on the dimension. So in particular, this is non-zero, okay? And this computation is due to Gromov, and there is an alternative proof by Thurston. And in particular, what you see now is, and this is also why this invariant is so interesting, there's a rigidity thing going on, right? So right, so on the right hand side we have something geometric. It's the hyperbolic volume of a hyperbolic manifold, and a priori there's no reason why this should be a topological invariant. But the left hand side is a topological invariant. It's a homotopy invariant. I mean, you can easily check this. It's a super easy computation. So in particular, the volume of hyperbolic manifolds is a homotopy invariant. And of course, I mean, we all know this. This is just Morse rigidity. Basically, it's a consequence of Morse rigidity. But what Gromov did is he gave an alternative proof of Morse rigidity, and it was based on considerations like the computation of the Simplicial volume. I mean, there are lots of other steps that go into this proof, but it's one of the steps where you see rigidity going on. So it's this topological invariant, somehow it has geometric content and sometimes can lead to rigidity results. Okay, and then also before we had this, like the antagonist of hyperbolicity is amenability. So if pi1 of M is amenable, well, and the dimension is non-zero. Okay, so this is a small print. Then Simplicial volume of M is always zero. So this is a vast generalization of this S1 case, right? I mean, pi1 of S1 is just the integers. That's an amenable group, and okay, so it holds for all amenable groups. This is a very, very strong statement, and this goes back to Gromov, and Ivanov gave an alternative proof with more algebraic methods. Okay, so maybe there's one case that I also should highlight here. So I mean, you can get it from this formula. You can also do it directly geometrically. There's one case of hyperbolic manifolds that are super important. Of course, these are the surfaces of genus at least 2. So what you get here as a Simplicial volume is just 4 times G minus 1. Okay. So as I said, you can derive it from this formula and I don't know, Gauss-Bonnet, or you just prove it by different means. But in general, one should be aware of the fact that this is very hard to compute. Okay. And there are not that many really concrete computations known. I mean, there are a few more than what I listed, but it's extremely limited. And also it's, if you want, it's also not computable in a strict sense, but also the class of known examples is rather small. Okay, so that was Simplicial volume of manifolds. So I will upload this page, and then we will come back to the one-relator groups. But that should also be pretty clear now how this will happen. So now we have something that we can apply to homology classes, and in the case of manifolds, we just applied it to the fundamental class. But this definition of taking the one norm of a homology class, of course, you can do it to any homology class that you find. So in particular, if you have a one-relator group and the relator is non-trivial and in a commutator subgroup, then you have a distinguished class and you can apply this, this norm to this class. And that's what we will do. So that's our definition. Okay, so let R be a commutator and it should be non-trivial. And then we define the simplicial volume of the one-relator group. As follows, so we denote it as in the manifold case. And what we do is we just take the one norm of the fundamental class of this one-relator group. And what's this fundamental class? So let's recall what we did before. I mean, we had this presentation complex thing, right? And then we had the two disk glued onto this wedge of circles by the relator. And this two disk, I told you that this defines a class in singular or in homology with integral coefficients, but also of course with real coefficients. And this is the class that we take. So this is a generator of this homology. Okay, so if with real coefficients, this is also isomorphic to R, and this is a generator. Okay, and that's the class that we will take. Okay, so yeah, I cheated a bit in the definition, so I smuggled some statement into this definition. Namely, I mean, the way I wrote it down, it's something that depends on the one-relator presentation, and indeed, this class will depend on the presentation, but the only indeterminacy that you have is assigned by ±1. So the one norm in the end will be the same. So this value is really well defined as an invariant of the group. Okay. So and the key example that we have in this situation, of course, again, is like the surface group case, right? So we have, if we look at the surface group case, so we have generators A1 up to AN and B1 up to BN. And as a single relator, we have this product of commutators. Yeah, of course, then this is the same as the simplicial volume of the surface of genus N, right? I mean, if you look at this construction, I mean, you just see that you get the surface of genus N, okay? And I mean, usually you don't draw it in this way. Usually you draw it in a different way. But okay, and we have seen above that I told you that, okay, you get 4 times n minus 1. So this is also true if n is 1. Okay, so you get this value. And then, I mean, before we started talking about the simplicial volume, we first talked about stable commutator length. So let's relate this to stable commutator length. And we can express this in terms of stable commutator length as 4 times. So the stable commutator length of this relator was just n minus 1/2, okay? I mean, I didn't prove it, but I told you that this is the result. So what you get here is that, yeah, so maybe let's give this a name, right? This is S and this is R. Then this is 4 times stable commutator length of R minus 1/2 in this case. Okay, so that's just putting these known results together. Okay, so somehow this example and some other examples made us ask the following question, namely, when do we have this equality? Namely, that the simplicial volume of this one relator group is really the same as 4 times stable commutator length r minus 1/2. Okay, and I mean, if this is true, then we also know how to compute the simplicial volume of one related groups efficiently, because I told you that you can compute a stable commutator length efficiently in the free group. So this would be very nice, but let's prepare for the case that maybe this is not true or we cannot prove it. So the related question is, can we compute this simplicial volume of the one related group? So how can this thing be computed? And as I told you, in general, for high-dimensional manifolds, there's no way of computing simplicial volume. I mean, it's completely out of reach. But maybe in this case, because we're in such an easy situation, then maybe one can do something. Okay, so what I want to do now is I just want to list some answers that we have. And these are all joint results with Nicolaus. So yeah, let's work with the things that we already have. So of course, I mean, we have that the answer to the first question is positive in the surface case, right? I mean, that's like the motivating example that I gave you. And maybe let's move further down the hyperbolic line. So if R is a proper power, okay, then I told you then the one relator group is hyperbolic. And then there is a result by Mineyev that tells you something about bounded cohomology and therefore also about the one norm. And so this simplicial volume is positive in this case. So this uses results of Mineyev. Okay, so this is like the counterpart to this thing that for manifolds in the hyperbolic case, we had positivity. Okay. So yeah. Yeah, one other thing maybe also, I should also say this here in this question. I mean, does it even make sense? But I told you that a stable commutator length has this gap of 1/2. So the thing that we have on the right-hand side is certainly non-negative, and that's good because the left-hand side is non-negative by definition. So, but that we have guaranteed. Okay, so then there are some positive results where we really have equality. So let's call this maybe star. So star holds if the relator R is decomposable. So, and I'll say what this means. So this means that the relator is either it's such a product R1 and R2, and the these two parts, they live on different generators. Okay. Okay. Or the other case that you could have is that R is such a mixed conjugation. I mean, it's not really a conjugation, but so it's R1 times T times R2 times T minus 1, and these two pieces, R1 and R2, do not contain T. Do not contain T. Okay. So okay, what does it use? This uses also lots of computations in bounded cohomology and results in stable commutator length of these decomposable relators by Caligari. Okay, so I'll upload this page and that worked. Okay, that's better. Okay, so this also has a nice consequence. So from these computations and further computations of Caligari of stable commutator length, you see that mod 1, all of the positive rational numbers occur as Simplicial volume of a one-relator group. Okay. Okay, so then do we have some general estimates that always hold? Yes, we have some estimates, but they may be not so impressive. So we have that always the Simplicial volume of the group is bounded from above by 4 times stable commutator length of R. So this is close to this equality in star, but not quite there yet. But this is also not so hard to prove, right? If you think about, back again, let me draw this once more, this presentation complex picture, right? Where you have here your D2 and here you have R. Now you can imagine that if you have a way of writing your relator R as a good commutator, then you get such a 4 times the number of things that you needed to write your relator, and you can use this as your disk and glue it there, and this will, this gives you a good representative of your class, right? And you just need 4G simplices. Okay, so this roughly gives the proof, and then that only proves that this is at most 4 times stable commutator length, and then you can fiddle around a bit and you get strict inequality. Okay, so we always have this, and from there one can do the next step. So asymptotically, star holds. Namely in the following sense, that we always have that if you look at the one-relator group, and now you can stabilize by the power of your relator, okay? And you can look at the limit for n to infinity, and you can do this to both sides of this hypothetical equality star, and what you would get is that then the right-hand side should be 4 times the stable commutator length of R, and this we can prove. So asymptotically, it's true. Then there's the further things. So by the computations of Caligari and Walker, you know the distribution of stable commutator length, like distribution in the probabilistic sense, and we can show that the Simplicial volume of the one-relator group that they has the same distribution as, not the same, but almost the same distribution as 4 times the stable commutator length. So they have similar distributions. Meaning that if you look at random relators with high probability, you get things that are very close to each other. Okay, so this uses the corresponding SCL results by Caligari and Walker. So this is really, it's just a matter of counting in the right way and reducing it to a small cancellation problem. Okay, and finally, yeah, I'm sorry, I need 2 more minutes. Finally, so I told you that for stable commutator length, there is a way of computing it in an efficient way. And we have something that is similar to that, but it's not quite that good. So what we have is there is a function, or yeah, let's call it a function. So we call it lalop for L1 version of scallop, because the original program is called scallop. This gives you a rational number. So this is similar to Caligari's scallop for SCL. And what does it do with the following properties? So whenever you have such a relator in the commutator subgroup, then we have that lalop is a lower bound for the simplicial volume. It is also a lower bound for 4 times SCL minus 1/2. And I mean, this is not spectacular, but it admits a polynomial algorithm for its computation. Again, in the length of the relator, and in many examples, we really have equality, okay? We have that lalop of R really is the same as this simplicial volume. Okay, and we use this extensively. I mean, this, you can use this in practice. We implemented it, we have 2 implementation, and there's also a faster version that is not as exact, but it's much faster. So if you're searching for things, then you can use it. And in fact, what we found is, after looking for a while, is that we have an example that does not satisfy star. So for a long time, we believed that star should hold and that we just cannot prove it, but it turns out that there are exotic elements. So let me just, for the fun of it, let me just write it down. So it's just, it's a certain relator, okay? And what we get as SCL in this case, so the capital letters are just the inverses of the lowercase letters. So SCL of this thing is 5/8. But yeah, and then you would expect that the simplicial volume is positive, but it's not, it's 0. And I mean, we found this example by computer search with this not exact thing, but then like the also the computer gave us a certificate with which we can check that actually, I mean, the simplicial volume is 0. Yeah, so this is an actual proof. You can check. You can even check it by hand. It's not that complicated. But finding the element, of course, is maybe not so easy. So let me just finish with one remark, namely, now this was all for one-relator groups, and maybe it's not so clear what this is good for, but we used very similar things to solve a problem on higher dimensional manifolds. So we solved the gap problem for simplicial volume of manifolds in dimension 4 and higher. Okay, I'm sorry for going over time, but now I'm done. Thank you.
Let's thank the Clara, please. Now, are some questions?
Well, I'd rather have a comment than a question.
Yeah, sure.
My comment is actually it is related to the first probably of this slide that it is comment maybe from for young mathematicians participating in the seminar, that there is one major problem in Pro-P groups is one relator question about one relator Pro-P groups, namely it belongs to Sir, right, who asked whether one relator Pro-P group without torsion has homological dimension 2, and it is widely open.
Okay.
And it is open even if sort of relator is finite, meaning that we can take just abstract group, one relator group, the group that was presented in this seminar, and make Pro-P completion of this. So supposing that it doesn't have torsion, right? Then the question whether it has homological dimension 2, this is still open also, and to solve this would be already a good advance in this. And one comment related to this, unfortunately, it is not true in the Pro-P case that if you have if your relator is not proper power, then the group is not torsion free. So this one of the problems. There is a counterexample. That's why the problem is actually formulated, I mean, like that the group has to be torsion free.
Okay. Ah, that's great. I didn't know this problem. That sounds great. Yeah. But I mean, we have obviously we have nothing to say about this.
Well,
But,
actually, to study one-relator abstract group, as I said, right, might give a hint what to do in the Pro-P case just by taking Pro-P completion. For example, if we take a one-relator with torsion, then Weiss proved that there is a hierarchy, like splitting, amalgamated product, extension, and so on. Right, and he proved that it is quite good. So in that sense, that in the profinite completion, the structure survives. In the Pro-P case, we don't. For Pro-P topology, we don't have this. So
yeah, but it's kind of
something like this would be extremely helpful. But this is not only the thought. So actually, the problem is solved because nobody has a good idea.
I can imagine. But so, I mean, one thing, I mean, I started thinking a little bit about it, but then I somehow dropped it, is there is a version of Simplicial volume where you somehow, yeah, you get into the profinite completion world, but you need the action of the group on the profinite completion. So what you can do is you can look at the stable integral Simplicial volume. So this is, you have, let's do it for the manifold case. You have a manifold, and then you look at all finite covers of the manifold. You take the integral Simplicial volume of the finite covers, and then you normalize by the covering degree. And this can be expressed in terms of a more probabilistic thing that involves the action on the profinite completion. So yeah, and then you can think about that. So but yeah, I mean, in the one-relator group case, I didn't really follow up thinking in this direction, because of course, if you have finite index subgroups of one relator group, then you somehow drop out of the world of one relator groups. So I wasn't sure what to do with that. But yeah, maybe it's worth thinking a little bit about that.
Some other question?
I have two questions, if I may ask. The first question is about the result that every rational between 0 and 1 equals the simplicial volume of a group, mod Z, right? Does the same hold for stable commutator length? Mod Z.
Yes, I mean, that's where the result basically comes from, because for these for stable commutator length, it's a lot more is known, and there are lots of explicit computations of explicit values, and there for decomposable relators, it's known that you can realize every rational mod 1, and we take it from there, because for decomposable relators, really we have the equality between both sides.
Okay. The second question was whether there has been some work to connect this with primitive of the relator.
We didn't do this yet. No, I mean, we somehow at some point thought, oh, this would be interesting to do it, but we didn't do it. So there's still a lot of work to be done. Yeah.
Okay.
Some other question? I would like to I have a question. If it's possible to define the simplicial volume when to have more than one relator, like two.
So
in the case of the Thompson group, like for example.
So the problem is, I mean, you can define this one norm for every homology class, right? I mean, whenever you have a homology class in real homology, then you can just say, oh, I look at the one norm of this. But somehow you need I mean, either you have to look at all classes at once, and then maybe you look at the norm one wall or something in this norm, semi-norm, or you have to have a distinguished class. So like in the case of manifolds, you have a fundamental class that somehow cries for applying it. And here also in the one-relator class with relators from the commutator subgroup, you have a canonical class to look at. So if you have a two-relator group, then I don't know. I mean, there's probably no canonical candidate for homology class that you could look at. So you would have to, consider all of them, or I don't know, make a choice which class to look at.
Okay, thanks. So if you don't have more questions, let's thank again Clara Löh, please.